welcome to this video on the data behind frontier large language models, where I want to go into a bit more detail into the type, the scale, and the diversity of the data that powers the latest models. So in terms of data, since already GPT-1 generative pre-training, their first paper, we've known that large-scale datasets are useful. Specifically in this paper, they demonstrated that very large gains on certain tasks could be achieved by first pre-training the model on a very diverse and unlabeled corpus of text. And since that paper, the pipelines have become a little bit more complex, while they still leverage the same idea of first pre-training on data that is available in large-scale web pages, books, papers, code repos, to hopefully inject the model with as much as possible relevant knowledge. Then we would mid-train to boost the performance on specific important application areas. It's a stage where we use less data, but the data is more high quality and domain-specific. And it includes, for example, instruction data and reasoning traces and so forth. And then we would also post-train, which includes at times still some supervised fine-tuning, but also a lot of reinforcement learning to actually get better at specific tasks. So if we want to understand exactly the kind of data that is used to build a strong model, the top labs are not going to be very helpful. They're relatively secretive as to which data they actually use. So on the webpage of OpenAI, all I could find is things like, select publicly available data, proprietary data from data partnerships, some human feedback from AI trainers, and so forth. And not even all open source papers share equal amounts of information about the data. So DeepSeek, a lot of interesting architecture and engineering insights, but less so on the data. Here I have 4 chunks from their 1 to 4 DeepSeeks, and basically all they say is, diverse and rich and high quality, but what exactly that means, who knows? Not only DeepSeek, same goes for some of these like GLM papers, for example. So my point is that while we see consistent improvements on the benchmarks, here I show, for example, terminal bench, and you see that basically since July 2025 to 2026, every model that has been coming out, so the date is the model that has been released on that date, the performance on terminal bench has been following an upward trajectory, so improvements are seen. But it sometimes remains hazy to understand how exactly this model actually learned to do this task. So was it just RL that worked? Did you also need some labeled SFT examples? Could you use another LLM to create data? Do you need a human expert? How many examples is enough? To what extent will the knowledge from the pre-training stage actually help, and so forth. And so here, I think it's fantastic that we have a lot of open models that provide a lot of insight as to the data that they use. They also release a lot of their data sets. OLMo-3, Nemotron 3 Super and Ultra, both I will use a little bit in this talk. They provide tons of detail on how they generate the pre-train and mid-train data. And I think these MAI-Thinking-1 and GLM4.5 provide also some interesting insights for the RL agentic stage. So first stage, let's look at the pre-training data. I think one thing that I found interesting here is that even though pre-training, as in the GPT-1 paper, was meant to be, use whatever information is available, it's unlabeled, but hopefully useful. The thing is that even at pre-training, if you read a lot of these recent papers, you sort of need to understand which evaluations you're targeting. So I would say that modern training is increasingly evaluation shapes. Even broad training phases are influenced by the tasks and benchmarks that we ultimately care about. For example, the OLMo-3 paper writes about how they create this OLMo-based eval benchmark suite that can support decision-making during base model development that targets a high coverage of capabilities, spanning math, code, medical knowledge, and so forth. But basically, already at this stage, you need to know a little bit, what am I training for? Related to that is also that even though we still use as much data as possible, we still also want clean, high-quality data that again matches the tasks that we want to get good at. So again, OLMo-3, but they show this pipeline in a very nice visualization as to how they actually go about filtering, cleaning, and shaping the training data. So they use common crawl web page data. They then HTML text extract, do some heuristic filtering, deduplicate, classify it into different topics and quality metrics. And same with these other academic PDFs, GitHub repos, FindMath, and so forth. And related to that is this fact that, again, whatever capabilities you're actually targeting in the pre-training stage will already significantly impact also your pre-training data mixture. So why do they do this topic and quality classification? It's because you want to have control over which topics you're actually going to include in the end, because this significantly matters for your downstream performance. And so this MAI-Thinking-1 paper, they have this nice plot where they basically trained 61 different mixtures. So every dot on this graph is a different mixture. And then they evaluate, in this case, in this plot, they show the web HTML validation loss and the code validation loss. And you clearly see that some mixtures perform less good than maybe other mixtures perform. So in this case, by the way, you want as low as possible a score. So the mixture is important. The mixture impacts how good your capabilities are going to get. But of course, because pre-training is so expensive and the model sees trillions of tokens over hundreds, thousands of GPUs, finding the right mixture is challenging because we don't have the time to, run different experiments to find the perfectly balanced mixture. So people use all kinds of heuristics and so forth to hopefully do a good job at this part. And then I also want to stress again that even pre-training becomes increasingly this kind of targeted capability construction, which, what do I mean with this, is that even already in the pre-training stage, you might decide to include specific capabilities you want to target. Here, Nemotron 3 Super wants to target Python problem-solving capabilities. To do this, they generate tasks around specific benchmarks, human eval benchmark datasets, and solve it with GPT-OS S120B to generate, in the end, 5 million problem solution pairs. But again, they know, maybe in some run they saw, hey, we're not as great in Python, let's already inject synthetic data generated by a stronger model, or at least a good model, in pre-trained stage. And the same thing in Nemotron 3 Ultra, where they said, okay, let's level up our model on legal knowledge. And they curated a lot of detailed, interesting data sets around legal knowledge to already inject into the pre-training stage as well. All right, mid-training stage. So the mid-training stage is basically continuing pre-training in terms of, it's still supervised fine-tuning, but here it's a cheaper stage that is also focused on more high-quality data. So if, for example, here in this graph, the pre-training stage takes 30 trillion tokens, the mid-training stages only take 3 trillion and 150 billion. So it's a cheaper stage. Maybe you can also experiment more with which skills and capabilities you actually want to inject. The data is synthetically created by prompting models. I will show you a bit more on this in a second. That really, again, targets specific skills. And I guess the core challenge in this stage is to build a model which will have skills that will then be useful in the reinforcement learning stage, where it will be the model that has to, find by itself a reasoning trace or a tool call trace or whatever you want to call it to get the rewards from the environment. But it's hard to say what these capabilities are. In part, they're very task-specific knowledge about certain things, but in part, they're also really general, like, the ability to critique, to reason, to reflect, and so forth. And how do you actually teach for those things? So the first thing that is also, the first specific thing that is important in the stage is also the long context extension. I think it was Dario Amodei in a video with Dwarkesh, where he said that, if a model is not properly trained on using N tokens, it will never be able to use the N tokens. So after you deploy it or in the RL stage, if it doesn't know how do I operate with reasoning traces longer or context lengths longer than what I've seen, I won't be able to do it. And so one big part is this long context extension, even though it's very expensive to train already in the pre-train stage, as this OLMo-3 paper mentions. On these long contexts, we only do this in the mid-training stage, and many different papers do it differently meaning different numbers of tokens, different context lengths, different types of tokens, and they also share their specific context recipe. Now, besides the context, there are also other target capabilities that you might want to target. Roughly, I guess this is similar for all papers, something in code, something in instruction following, something in math, something a la reasoning, some safety behaviors, but the details differ a little bit. I won't go through all of it exactly, but you can check the papers as well. And for example, Nemotron 3 Ultra uses, as I said, long context SFT data, safety behavior, search trajectory. So, how does some model actually perform a certain search assignment, synthetic agentic trajectories with terminal tasks, software engineering, and so forth. Tasks focus on resolving real-world GitHub issues, math and science, multi-turn chat SFT, coding problems, CUDA, multilingual capabilities. I'll go in a bit more detail on all of this in a second. And then there's the OLMo-3 paper, and they also provide huge amounts of super interesting details. So they target general purpose math capabilities. They also synthetically create variations of a benchmark, the math benchmark, use code solutions, English solutions, discussing it, use other data sets that have cleaned already mathematical web data, some fill-in-the-middle coding tasks, lots of Q&A tasks, cross-domain instruction data sets. And the thing that I find very interesting is, besides very task-specific things that they inject, so hey, this is the task, variations of this task are performed in this way. That is a big chunk of the data sets used in mid-training. They actually also decided to inject kind of meta-reasoning tasks, which aren't things a la, this is how you solve 3 + 3, but it's more around general tasks that you would need, capabilities that you would need to solve 3 + 3, and I'll go also into that in a bit more detail in a bit. Take a quick look at how this data is actually created. So this is the Nemotron 3 Ultra paper. Super also contains many interesting insights. But so yes, they write something about long context, efficiency and control, safety, search. So this one is, for example, interesting. So they include a commercially clear subset of open researcher, a public SFT dataset designed for long horizon research agents. It is basically 100K trajectories of search using GPT-OSS 120B, so a bigger, stronger model, as the teacher model. And then basically, you kind of, this dataset is on Hugging Face. So if you look through how it looks, you will see that you see the agent do search tool calls such as search or open or find, and then reason about the information that they see, all to then finally answer the specific search question, like, what is the information that you can find about blah, blah, blah. But so again, lots of tasks. What is it that they say? 21 SFT trajectories of another model performing these tool calls, and that is provided to our model as examples. They do similar things with this terminal use capabilities. For example, they use this, I should be precise, they seed their instructions from a combination of publicly available datasets, open code reasoning, SWE bench, and so forth. So they basically start with benchmarks or tasks that someone at some point curated that we know we want the models to get good at. Around this series of tasks, they then synthetically generate variations of it with another model. And then they use also, I guess, DeepSeek v3.2 as the model to solve these specific tasks. So we know what we want to get good at. We generate tasks in that environment, and then we solve these tasks with a stronger, or at least, again, a good model. And this is the data on which we SFT our model. Same thing with software issue resolutions. They, what is it that they do? They curated a data set of agent trajectories resolving real-world GitHub issues, math and proof data, science, chat, code. I also found this one interesting with the CUDA kernels. So I guess a big focus of some labs is to also create AI that builds better AI, and kernels is one of those things. So they here also constructed a large synthetic CUDA dataset comprising of 100K samples of how to do kernel generation, repair, and optimization, because it seems realistic that the models could do it, but only if we really show it also a lot of examples of how to actually go about doing certain things. So that is that. Now, what I want to say with this is basically this. Once a scale becomes measurable, then is, in my view, when it also becomes trainable. So a big part of the mid-training and partly also the post-training stage is to really identify this, even maybe a bit the pre-training stage, is to identify specific scales that we want the model to improve on, these skills are often derived from benchmarks or target evaluations, which is why, when a benchmark is released, soon the models get good at it because we can dissect which specific skills do we need to solve this, generate tasks around it, sometimes solve them with humans, sometimes solve them with other models. And then we basically SFT our model on these traces to get good at this, in the hope that, again, by targeting the right skills, the SFT stage will teach the model to be good both on solving these tasks, but also be good at tools and strategies and recognizing patterns and reasoning that will be useful in the reinforcement learning hill climb stage. And so the core challenge for building a model that would really self-improve is that you might at some point have to stop being so specific about the skills you wanted to get good at. So sure, you're like saying, hey, this is a series of tasks I want you to get good at. We dissect these tasks with quite a lot of human efforts. We generate tasks around it with partly human, partly synthetic data, and then we see improvements. But again, for this self-improvement to really take off and for models to really continue learning and be good at learning on tasks that we haven't curated so specifically, we want them to extract general reasoning skills. And I think, again, that's why the OLMo-3 paper I thought was really fun, because they included this meta-reasoning data set. So basically these capabilities such as self-awareness, evaluation, backtracking, conceptual reasoning, and so forth, that might be useful to solve math and coding tasks. And they say that this actually helps in the performance. In itself, it is not an easy thing to do, because even for humans, we don't necessarily always know what does it take to educate or teach humans such that then on the job they can be very strong and good performing. Is it purely, having them do hundreds of maths examples, or should we be teaching also other things? It's tough to say. And I guess we're at a stage where also with AI models, we definitely see the recipe of this is the task, let's generate tasks around it, or let's dissect the skills necessary, and then we teach the model to do it. We see that there are mechanisms, that this mechanism basically works, but it's still very task specific and still, I guess, a work in progress for also how we can streamline this. Final thing, post-training. So a reminder of what is post-training. It's basically this stage where we want the model to get better at I guess an iteration of even more advanced and real-world tasks that can be verified through some environmental feedback. So that means that in this stage, data generation is primarily task generation, creating a large number of solvable tasks, starting with, again, some seed tasks, and also environment generation. For example, in mathematics, you might say, oh, the answer is 8, and you might just have the model check, is the answer that you might just have some little code that checks whether the answer that the model generated is indeed correct, an exact match with your ground truth. But if you want much more involved agentic tasks, it is really critical to build these environments in which the agent can act and receive feedback from this environment to know, to either collect more information and in the end to also know did I complete the task or not. So a big focus of the recent papers is also on creating these environments. So several examples of how we actually create these task environment pairs. In the GLM5 paper, they have some interesting details around it. For example, when they create software engineering environments, they collect a large corpus of real-world issue pull request pairs and apply a rigorous rule-based and LLM-based filtering to ensure we have high-quality issues. And then they use this framework called repo launch to actually construct this environment around it. And I think, again, this is a place to maybe stress that I think it's very cool, the stage that we're at. Before, we were at a stage where, again, humans were annotating certain answers and so forth, and we were just SFTing on this data. And now we are at the stage where we curate certain tasks and then have the model perform them in an environment that we replicated or created or built, where it can get feedback in many different ways, and then it has to kind of get to the answer itself. And I think it's interesting. The core is to construct, as I said, high-quality solvable tasks. So here they also speak a bit about terminal environments where they want terminal agents. They have this agentic data synthesis pipeline where they create task drafts, then concretely implement the task, and then kind of iterate on the task. So the core thing really in this stage is to also build good tasks where you could also build an environment which you can then let the agents operate in. And the core thing is also to have the tasks be not just high quality and solvable, but also frankly challenging. And here in their search task, they say, okay, for deep search information seeking tasks, again, data synthesis pipeline that produces challenging multi-hop Q&A pairs that require multi-step reasoning and so forth, that is grounded in multiple web sources. And they also apply this difficulty filtering and verification to, again, ensure that we have tasks that make sense and are sufficiently challenging. So then another paper that I think is very interesting to highlight is this TMAX paper, which is around constructing a data set for terminal agentic tasks. And I think what it highlights is that training agents on specific tasks really, again, requires large-scale and diverse related tasks. Okay, I've said this now a few times. What does this paper want to do? They want to get good at Terminal Bench 2, which is roughly 90 problems across software engineering, machine learning, security, and data science, and a few other things. And this paper designs this kind of data creation pipeline where they decompose certain tasks that you would want to certain skills that you would want to have inside your task. And then through that, they create these tasks and corresponding environments. And then they show that if we actually train on this data set, so they took some time to curate this specific task environment data set. And then they RL on these 15K samples for 2-3 days. And then they show that they can achieve 27% on Terminal Bench. So, two interpretations of this. On the one hand, I could say that this really makes very precise what it takes to get good at a benchmark or an evaluation or a specific task. If I have defined just 90 tasks that I would want my AI to do, it is possible to define this pipeline with quite some work. It would take quite a lot of tasks, 15K, and it would take to then, RL on a few nodes for 2-3 days to actually get not even to full performance, but at least to 27% performance on this. So again, all of the training is in a way still very task specific, and a lot of effort has to go into dissecting what makes us good at this task and generating data around that. On the other hand, I also think it is a very positive interpretation, because it is pretty cool that we have gotten to a stage where we can take models of, I think in this case, 8-9 billion parameters that have enough pre-trained, supervised, fine-tuned knowledge for certain skills, such that if I know what I want my AI to get good at, I can define this data pipeline. I can generate tasks and environment pairs, such that then for only 2-3 days, for only 15K tasks, I can actually get some performance. Yes, 15K is a lot. Yes, it might be less sample efficient than maybe a human would need. But at the same time, I think we could appreciate that we are at this stage where we do have these pipelines that at least seem to work. We have a recipe that at least begins to make sense. Yes. At the same time, I think this also shows how task specific we still are, so that, these ideas of AI doing everyone's job, I think will be still challenging, but I'll get back to that in a bit. So, yes, well, I'm getting back to it a little bit now. So a lot of the stories around these AIs kind of really self-improving outside of just the tasks that they're trained on, would require that the models learn very generalizable skills. So not just skills that make them good at this task, but also skills that would then apply to another task. And the question is, do we see any kind of evidence of that? So in the Nemotron 3 Ultra paper, I found this table where they have teacher models which are very good at a task, and then they have the student model, which, let's look at the MOPD2 column. And my question was, does the student then actually ever end up exceeding the teacher? And the answer is yes, in 2 cases, in Terminal Bench 2.0, student 54%, teacher 50%, and in this multi-challenge benchmark, which I'm not sure what that exactly is, student 63.8 and teacher 63.3. And the paper themselves notes that, on several benchmarks, the student surpasses the teacher, suggesting positive cross-domain generalization emerging. So something the student learns on some other kind of task managed to be useful on this particular task, let's say. But I would say it's still really very limited. Even in tasks that are related, these are all frankly coding questions, this generalization is very, very limited. So how realistic is it really that in a very short amount of time, or even a few years, maybe, I don't know, we will have frameworks and models that can by RLing, by SFTing, by whatever, learning a specific series of tasks, also somehow start to perform on other tasks, I think it's something we should question a little bit. And so, to conclude, what are the lessons that I want to communicate if you've made it this far in my video? I think progress still depends very critically on knowing which capabilities to train for. So once we know what we want the model to get good at, once we have released, for example, a benchmark on this task becomes measurable and hence it becomes trainable. So again, this is why when a benchmark is released, in a few months, we quickly see the model start to get good at this particular task. Related to that is that training remains very task specific. So even when the goal that we would want from these AI agents is very broad general capabilities, the actual training process, so the actual way in which we get models to get good at specific tasks, is still designing the specific tasks and making concrete which skills are inside that task, and then generating very, very, very many tasks around that domain. And this is a process that takes time and effort. So again, I think this slows us down on this trajectory of like, AI will take everyone's job tomorrow. I think for self-improvement to take off, so again, for AI to start getting good, or even, for to have AI that continually learns on the job, that would be able to take my feedback and in several months, just like a human intern, improve into a much better employee. The hope right now is that training on very specific tasks which we can RL for, tasks which we can make precise, would somehow teach reusable tools, reasoning patterns, search strategies, reflection, decomposition, lesson extraction, and so forth. I would say right now the evidence for this is limited, since we cannot even properly generalize across related domain tasks necessarily, as I showed you in this Nemotron 3 table. And I would also stress that there is still the need for a teacher. So in a lot of things that I showed you, there was a teacher model that was creating these supervised reasoning traces. But that means that at some point, maybe also a human was involved in doing some of those things. Yes, and I think also RL really hill climbs most effectively when the model has already been exposed to these relevant solution traces or strategies. So we're still reliant on these teachers. Right. I will end it here. Thank you for making it so far.